This is the last section in chapter 6. Areas of surface of revolution. What does that mean? Well, we know the surface area. So, for example, let's pretend we had a jump rope and it's rotating about this axis. Whenever you spin a jump rope, just where the rope is itself, that is the area of the surface, and the rotation is the around the axis. So, in other words, we're not looking for the inside, we're looking for the volume of this. We're simply looking at pretty much the shell. What is the surface area of that shell? So let's look at one slice of it. Let's look at one slice of it. We're only going to look at this part right here. What we have to do now, we have to build our formula. It's going to be similar to one we just used in the last section or earlier this chapter. If you think about it, what did we do in the last section? What were our calculations in the last section? What was our formula? Length of the curve, which was right. And that's what the entire early part of this section was about. It's now, how does this, and we also talked the last part of the last section dealt with the surface, the arc length. Now, how does that relate to here? Well, what we just did there is we found this arc length right here. Or if we use the length, we use the straight length between the 2 points. Let's say this is P and this is Q. So now that's the first part. So we'll have to use this formula for that. But what else do we have to do to find the area of this? Now it's this entire skin of the outside. How do we find that? What do we have to put inside there? So the area of that. So we have, first off, it has to be around the axis. So it's 2 pi. We have to have the height, which is our f of x. What else do we need to know? The length. Is there anything else we need? The what? We said what? No, because this length, the width wouldn't work for us. But that's a good thought, but that wouldn't work for us. No, all we look for is the outside. There's just the outer shell. Is what? Well, that's what 2 pi r. This is the 2 pi. This is the length. So this is 2 pi r. The radius of this is this function. Okay, so that's pretty much what we need. Now we got to start building from there. F of x, we have to now look at 2 points. So we have 2 pi. So that's going to be f of x k plus 1 minus f of x k. Because all depends on what our x's are. This is x sub k. This is x sub k plus 1. and the length. The length is this whole formula. Oop. Look at that. We're trying to get to it. So, but one of the problems we're going to face with is this one right here. Well, another thing. Remember how we defined length to begin with? Last section? And then we defined dy dx. That's our derivative. So this is what actually goes in there. So what we have here is delta x squared plus dy delta x. We can multiply delta x to both sides. So since that's x squared, this is x squared. We now have 1 plus dy delta x, or the derivative, I should say, which is what we got this from. But what is the problem with this one here? If we look at very closely, this arc length right here, whether we use the arc length or L, the problem is what? The gap, this opening right here. So how did we do it when we first started doing? Remember when we started taking delta x's, delta y's? What did we do to find the area? We took it either inside or outside, right? Neither of those worked, so we did what? The midpoint. So that's what we have to do with this. We have to take this at some midpoint between there. Times our L. Okay. Now that's only one section. That's only one section of our surface area. We have to now take all of these. How do we do that? To find the area, we got to take the summation How do you find the average? Remember, this is the average, the midpoint is the average. How do you find the average? We take f of xk plus f of xk plus 1 and divide by 2. So that's what this one's all about. Why is that important? Because if we look at it, this two and this two cancel. Okay. What are we trying to build here? Or what are we building here, say? We're trying to get the pieces together. Because now this adds up all the pieces at a certain length. How do we put them all together? So depending on what n is, and so this formula, remember that's our midpoint. We're trying to get to the Riemann sum because what this finds is each individual one. We're adding them all together. Well, what happens when this goes to infinity? So if we take the limit now as n goes to infinity, what does that give us? Infinitely small pieces. We can now find each of those bands around that object. But actually, I should, because we still have to keep this, we still have to keep that there right now. Because remember, this is the average. It's the midpoint. That's where I have f of c. What does this become by the Riemann sum? The limit of the summation of this function. What does it become? The integral. So the limit as n goes to infinity of the summation as k equals 1 to n of 2 pi f of c k times 1 plus y prime squared delta x. That becomes our surface, which goes from A to B, 2 pi f of c, or f of x, because now we're doing to take the integral. 1 plus y prime squared dx. So since we're only looking at the surface area, since it's 2 pi, it's going to give us the entire surface area of the rotation. So this is our formula we'll be using from here on out. Example 1. It says, find the area of the surface generated by revolving y equals 2 square root of x on the closed interval 1, 2. About the x axis. Okay, now let's first look at the question. Because remember, as we go through this book, through this course, we're going to have different questions and a whole bunch of different formulas. Find the area of the surface generated by revolving a function. Find the area of the surface, only the outside. Find the area of the surface generated by revolving a function. So that's why it's 2 pi, it's around. So it's a surface area, S. And so that we have to use this formula. Let's plug everything in there. What is A? What is B? A is 1, B is 2, because it usually goes A to B. In our case, it was like this, and which is the same thing as it's a closed interval. They can be given to you both ways. Or it could be spread out saying, find the surface, the area of the surface generated by revolving it from between x equals 1 and x equals 2. So it can be given to you many different ways. So we have 1 to 2, 2 pi. What's f of x? Our function, 2 square root of x. So now we have to find the first derivative for the inside. So x to the power 1/2. Bring the power down and subtract 1, which makes it negative 1/2. So y prime, the 2's cancel, is 1 over square root of x, or x to the power negative 1/2. So that goes inside here. 1 over square root of x squared. So we have it set up now. Remember what we did last time? Let's start. We have to first find this one. So we have to build from it from the inside. So 1 plus 1 over square root of x squared. We're going to do this one first, inside here. Distribute. We get 1 squared is 1. The square root and the square cancel, so we have 1 over x. So 1 is the same thing as x over x. So we have x plus 1 over x. So this goes back inside there. So now we have the square root of x plus 1 over x. We can split those. So what do we do with that now? Where do we go from there? Well, let's see. Let's take this and plug it back into our equation. One to two. We have 2 pi, 2 square root of x square root of x plus 1 over square root of x dx. What can we do inside there now? The square root of x and the square root of x cancel. 2 times 2 is 4, so we have 1 to the power 4 pi. And then now we only have to worry about that one radical there. This is a constant. It could be taken outside. Now we can take the integral. Remember, this one is the same as x plus 1 to the power 1/2. What's the integral of that? Well, we have to add 1 to that. X plus 1 makes it 3 over 2, divided by 3 over 2. And the derivative of x is just 1. So what happens with this? This flips. So this integral becomes 3 over 2 x plus 1 to the 3/2 from 1 to 2. The constant can go out in front. So we have 4 pi times 3 over 2 x plus 1 to the 3/2 from 1 to 2. 2 and the 4 cancel. 2 times 3 is 6. Oops, I had it backwards. It's 2/3, not 3/2. I had it flipped. Should be 2/3. Nothing cancels. So we have 8 pi over 3 plug in 2 plus 1 to the 3 halves minus 1 plus 1 to the 3 halves. We have 8 pi over 3. 3 to the power 3 halves minus 2 to the power 3 halves. We can't do we can't square root either of those. So we just end there. So it's square root of 3 cubed minus square root of 2 cubed. Which becomes 3 square root of 3 minus 2 square root of 2. And there's your answer. It's exact. The only thing different between this and what we did earlier was we have 2 pi in front. And the function itself. It's not that much of a difference. As it showed here that it helped us having the 2 square root of 2 up there, square root of x. Okay, now what about revolutions about the y-axis? We just did one about revolution over the x-axis. Now let's look at what they look at on the y-axis. Let's see what changes here. Instead of A to B, it becomes what? C to D. The 2 pi stays the same. Now we have a function with respect to y. 1 plus f of y prime squared dy. I should have used g instead of f because usually we use f of x. I should use g of y. Oh well, but so in other words, if you get an equation that looks like this, y equals square root of x from 1 to 4, you have to change this now because the function has to be with respect to x. So we have to change this one to x equals y squared. And now the new bounds are going from 1 to 2. But so we have to do what we've done earlier in the course. So let's look at example 2. The line segment x equals 1 minus y on the domain 0 to 1, which is 0 is less than equal to y is less than equal to 1. Is revolved about the y-axis to generate the cone below. Find its lateral surface area, which excludes the base. So we have -1, 1, and 1. And it's rotated about the y-axis. So that's what it's going to look like. A cone looking like this. So to use our formula, how many things do we have to determine? Look at our formula. We have to determine a C, determine a D, the f of x, or the f of y in this case, and the first derivative. We have 4 things we have to find. Then we can plug them in. So what is C? What is D? What is f of y? And then what is the first derivative of f of y? So what's C? And C is 0. D is 1. F of y is 1 minus y. It's our function. So the derivative of 1 minus y, minus 1. So now we have everything we need for our formula. Integral from 0 to 1 of 2 pi, 1 minus y, square root of 1 plus -1 squared dy. -1 squared is 1, so we have 1 plus 1. One plus 1 is 2, so we have square root of 2. Our constants can go out in front. 2 square root of 2 pi, the integral of 0 to 1, 1 minus y dy. Why does 1 minus y have to stay together? Why can't I take out the 1? Can I? No, it's this equation has to stay together. No, but at this point, I can distribute that integral to both of those if I wanted to. Or I can just take integral of this. So what would the integral be? So what's the integral of 1? Y. What's the integral of y? Y squared over 2. from 0 to 1. So we have 2 square root of 2 pi. One minus 0 minus 1 squared over 2. No, it's 1 minus, I'm sorry, 1 minus 1/2. I messed up there. I was looking too far ahead. So it's 2 radical 2 pi. So I have 1 minus 1 squared over 2 minus 0 minus 0 squared over 2. So that disappears, that becomes 0. So we have 2 square root of 2 pi. 1 minus 1/2. One minus 1/2 is 1/2. The 2 and the 2 cancel, so I have pi square root of 2, or square root of 2 pi. What do y'all think? So far, doesn't it just seem like it's a bunch of plug and play? But you have to be careful in which formula you plug it into, because that comes from the question that's being stated. If you have to rotate it around an axis, then we need to have 2 pi. If you don't, if you're not rotating it, then you know you don't need it. All right, that's it for that section, that chapter. The chapter is done. End of chapter 6.